How to get p-values less than 0.05 in biological research. Chapter 4. Outliers or non-normal distributions. Wilcoxon and Kruskal-Wallis rank tests. If you have outliers in your data, or the data within each treatment group are not normally distributed, t-tests are more likely to give non-significant p-values. Outliers and non-normal distributions reduce the power of t-tests to detect significant effects. Even when graphs of your data show that there is a difference among the groups, you may get non-significant p-values from t-tests as a result of the outliers or non-normal distributions. In these cases, rank methods and robust methods are alternatives to the t-test. We'll begin with some of the commonly used rank alternatives to t-tests and ANOVA. We'll see examples of each of these shortly. However, none of these methods allow you to have more than one explanatory variable. For this reason, I suggest that instead of using these methods, you consider the methods that allow for more than one explanatory variable described in the following chapter. If your sample size is large, deviations from normal distribution may be less of a problem for t-tests and ANOVA. However, even with a large sample size, you can often increase power by using a robust method or rank method. As an example of what we mean by ranks, here are observations from the sleep data frame, from R with the original values of the variable extra and the values of extra converted to ranks. You can use the help sleep command to read a description of the dataset. Alternative to two-sample t-test, Wilcoxon rank sum for two independent samples. Let's start with an example where we use a t-test for the question, do colon cancer patients have elevated level of the mucin protein in their blood? In this synthetic data, we have the level of the protein mucin in two groups. 1. Patients with colon cancer, and 2. Healthy controls. The two-sample t-test is commonly used for such data. Here is the R code. Here is the data. Here is the graph. The box plot and data show that there is complete separation between the two groups. In fact, all the cancer subjects have lower mucin values, 98 or less than any of the controls, 99 or greater. But notice the large outlier in the control group where one subject has a mucin value of 141. Here are the means and medians of the two groups. Notice that the mean of the control group, 109.4, is larger than the median, 103. This difference is due to the outlier. Here is the ordinary two-sample t-test using the R function t-test. The box plot and the data show that there is complete separation of the two groups, but the p-value for the t-test is not significant. P equals 0.05389. The reason that the t-test is not significant is the large outlier. The outlier increases the standard deviation, which increases the standard error, which gives the non-significant p-value. The output from the t-test includes the means of the two groups, 90.6 and 109.4, and the 95% confidence interval for difference between the means of the two groups, minus 37.99 to 0.399. Because the 95% confidence interval includes 0, we get p more than 0.05. The Wilcoxon rank sum test is an alternative to the t-test. The Wilcoxon rank sum test uses the rank value of each observation, rather than the actual value, so it is not affected by the outlier. Here are the rank values of the original observations. Here is the Wilcoxon test using the R function Wilcox test. Using the rank values, the Wilcoxon rank sum test yields a p-value of p equals 0.0079. We reject the null hypothesis and conclude that colon cancer patients have mucin levels different from those of healthy controls. The output from the Wilcoxon test includes the sample estimate of the difference in location, which is -13 for these data. The difference in location, the Hodges-Lehmann estimator, is the median of all pairwise differences between the two groups. That is, we calculate the 5 times 5 equals 25 pairs of differences between each value in the cancer group and each value in the control group, and then take the median of those 25 differences. The 95% confidence interval for the difference in location for these data is -51 to -5, the Moses confidence interval. Because the 95% confidence interval does not include 0, we get p less than 0.05. The Hodges-Lehmann estimator is not necessarily equal to the difference between the medians of the two groups. As described below, there may be no difference between the group medians. But if one group tends to have higher or lower values than the other group, stochastic dominance, the Wilcoxon test can give p less than 0.05 even if the medians are identical. Sample size required for a t-test to give power of 0.8. What sample size would we need if we wanted to get a significant p-value for the t-test for the colon data? The difference between the group means is delta equals 109.4 minus 90.6 equals 18.8. The standard deviation in the control group is SD equals 17.8. We'll use the usual significance level, alpha, of sig level equals 0.05 and desired power of 0.8. The function power t-test gives the required sample size for these assumptions. We would need a sample size of 15 per group, 30 total, to have an 80% chance of getting p less than 0.05 using a t-test. The chapters on sample size and power provide more explanation. Alternative to paired t-test, Wilcoxon signed rank test. The paired t-test is often used to test for difference in paired, matched samples, such as the difference before and after treatment. The Wilcoxon signed rank test is a rank-based analog of the paired t-test. Here's an example. Suppose we would like to know if bears lose weight between winter and spring while they are hibernating. We collect the following data. Here is the R code. The graph of the weight change shows that there are two large outliers. We'll first use the paired t-test to examine the change in weight of bears, where the same bears were weighed in winter and in spring. The paired t-test gives p equals 0.057, indicating that bears do not lose weight while hibernating. Then we'll analyze the data using the Wilcoxon signed rank test. The Wilcoxon signed rank test gives a significant result, p equals 0.0078, indicating that bears lose weight during winter hibernation. Notice that all the bears actually lose weight. Using the paired t-test, the p-value is not significant, and we conclude that bears don't lose weight. The Wilcoxon signed rank test gives us p equals 0.0078, so we reject the null hypothesis and conclude that bears do lose weight. Rank alternatives to one-way ANOVA, Kruskal-Wallis and R-fit. One-way ANOVA allows us to compare two or more treatment groups. The Kruskal-Wallis test is one rank alternative. Another alternative is the rank-based one-way R-fit function from the package R-fit. We'll use the quail dataset from the R-fit package. 39 quail were randomized to one of 4 treatments for lowering low-density lipoprotein. The variable, treat, is a factor. The variable LDL is the low-density lipoprotein. The box plots suggest that there are differences among the 4 treatment groups, but there are large outliers that will adversely affect t-tests, or ANOVA. Here are the median values for each treatment. We'll begin with a standard one-way analysis of variance. The one-way analysis of variance indicates that there is no difference among the 4 treatments. P equals 0.345. Next, try the Kruskal-Wallis test. The Kruskal-Wallis test approaches significance with p equals 0.066. Alternatively, we can use the function one-way rfit from the rfit package to perform a rank-based analysis of the quail data. The one-way rfit function indicates that there is a significant difference among the quail treatment groups p equals 0.016394. The one-way rfit output also shows pairwise comparisons that test for differences among the 4 treatment groups. By default, there is no p-value adjustment for multiple hypothesis testing. We can request estimates of the differences between each pair of treatments with confidence intervals adjusted for multiple comparisons by specifying method equals Tukey. For the pairwise comparisons, if the lower and upper bound CL do not include 0, then the pair of treatments differ after Tukey correction for multiple hypothesis testing. Thus, in the first row, which compares treatments 1 and 2, the lower and upper confidence bounds are minus 47.29 to minus 0.27, which does not include 0, so the difference is significant. Do the Wilcoxon tests and Kruskal-Wallis test compare the medians of groups? If the treatment groups do not differ in shape, but differ only by a shift in their location, then the Wilcoxon tests and Kruskal-Wallis compare the medians of the treatment groups. If the treatment groups differ in shape and location, these rank tests compare the entire distributions of the groups, that is, the ranks of all the observations, not just the median. You can construct 2 treatment groups that have identical medians, but that differ in their rank sums, and will give significant differences in the Wilcoxon or Kruskal-Wallis tests. The medians of the groups are both 0, but the standard deviations shape are different. The Wilcoxon rank sum test gives p equals 0.014, indicating that the 2 groups are significantly different. This result shows that, although Group A and Group B have identical medians, they differ in scale, standard deviation, and differ significantly according to the Wilcoxon test. In this situation, the Wilcoxon test is said to be a test for stochastic dominance, which means that one group tends to have higher values than the other group. A caveat is that the calculation of the p-value for the Wilcoxon test assumes treatment groups do not differ in scale, but differ only by a shift in their location. When should I use t-tests and ANOVA versus rank methods? T-tests and the classical rank methods we looked at in this chapter may sometimes be sufficient to get good results. Their weakness is that these tests only allow for one explanatory variable. For most analyses, you are more likely to get p less than 0.05 if you include additional explanatory variables in an analysis of variance, or if you use the robust and rank-based methods described in the next chapter. However, it is still informative to compare t-tests and the rank tests. The Wilcoxon, Kruskal-Wallis tests don't require the assumption of normal distributions and are not affected by outliers, so why don't we always use them instead of t-tests and one-way ANOVA? There are several considerations. If the data are exactly normally distributed, then ANOVA and t-tests have slightly more power to detect differences than do the standard versions of the rank test. However, even with small or moderate deviations from normality, the rank tests will usually have power equal to or greater than the power of the tests that assume normality. When the data within treatment groups is substantially non-normal, the rank tests will pretty reliably have power equal to or greater than the tests that assume normality. When you have a very small sample size, 5 or less per group, it may be mathematically nearly impossible to get a significant p-value using a rank test. But it may be possible to get significance using a t-test or other parametric test. One criticism of using rank methods used to be the difficulty of calculating confidence intervals. Before modern computers existed, getting confidence intervals for rank methods was harder than for methods that assume a normal distribution. But with today's computers, it is easy to get confidence intervals for rank methods. Visit mwalkerstatistics.com to download our code for all examples and get the free companion book in PDF format, or order a copy from Amazon